Hello, my name is Pan Zhenghao and I would like to introduce our work, DiffSCI, zero-shot snapshot compressive imaging via iterative spectral diffusion model to you. We will present our work in the following order: introduction, proposed network, and experimental results. Snapshot compressive imaging, or SF for short, consists of two parts: hardware encoding and software decoding. As shown in Figure 1, the encoding process is to modulate different channels of given 3D data with different masks and accumulate them element by element to obtain the final compressed 2D measurement, while the decoding process is to reconstruct the desired 3D data by the encoded measurement and the given masks through a specific reconstruction algorithm. For Spectral SCI, the most commonly used hardware system is Cassie system. Data cube of lambda n spectral bands are modulated by a fixed mask and shifted by a disperser, ultimately accumulated pixel by pixel on an image acquisition device to obtain compressed 2D measurement. The SCI system obtains the final 2D compressed measurement by modulating the current hyperspectral image with masks and acquiring it with camera compression. Firstly, the reconstructed initial value is obtained by multiplying the measurement and the given mask element by element and shift back operation, and then it is used as the input of our DiffSCI, and the reconstructed multispectral image is obtained through the iteration of PMP and diffusion denoiser. The diffusion model is pre-trained on RGB, and the reason for this is twofold. First, since hyperspectral images do not have a massive dataset like RGB for us to train a diffusion model based on multispectral images. The second, training a diffusion model on a dataset of only 3 channels like RGB requires a lot of time and effort. The diffusion model requires a lot of source and time, and there are usually thousands of bands on hyperspectral image, so the amount of training resource requiring will be even larger. However, directly applying the pre-trained diffusion on RGB images directly to hyperspectral images may face three problems. First, mismatch in the number of bands. Second, wavelength mismatch problem. And third, longer sampling time. Next, we will address these problems in turn. In order to solve the problem of mismatch in the number of bands and wavelengths, we adopted 3 different methods for testing. The first is overlapping bands method. For example, we sequentially select 3 non-overlapping bands CK and CK plus 1 to be fed into the diffusion model, and then we get reconstructed 3 bands, so that we only need to take 10 times diffusion to get the reconstructed hyperspectral data. However, this method neglects the data correlation modeling in multispectral data. For example, there will be a band jump between BI plus 1 and BI plus 2, which affects the quality of the reconstruction. So we proposed to conduct spectral correlation modeling experiments to fit the 3 neighboring bands into the diffusion model and get the reconstructed intermediate band after reconstruction. However, due to the wavelength mismatch between the RGB image and the hyperspectral image, which lead to a poor reconstruction effect of the part that divides from the RGB wavelength, while the reconstruction effect of the part close to the RGB wavelength is better. Therefore, we propose a wavelength matching algorithm to obtain the reconstructed image of ith band. As shown in the lower left figure, the wavelength matching method brings a huge improvement in PSNR and symmetric. However, the wavelength matching algorithm requires 30 times of diffusion sampling for a hyperspectral data with 30 bands, which greatly increases the sampling time. So, we propose an accelerated algorithm. The final sampling time and reconstruction results are significantly improved. The acceleration algorithm mainly uses the idea of residual accumulation by introducing the additional variable y1 to accumulate the residuals to get the effect of Nistov-like acceleration, thus improving the performance while reducing the time required for sampling. As shown in the table, on the comparison of Pearson R and the C metrics of our DiffSCI method on 10 simulated datasets, our method has a large advantage over the current SOTA self-supervised and zero-shot method, and compared to the supervised training, our method can still achieve leading performance on some data. As shown in the left figure, for the local patch of simulated data S1 and S2, it can be seen that our proposed DiffSCI method has a more obvious advantage in edge sharpness compared with others, and the reconstruction of the darker region of S2 can show the advantage of the generative ability of our method. As shown in the right figure, the spectral quality curves shows our method is able to achieve better spectral quality and surpassing the current SOTA methods. On the real dataset, our method also achieves better edge sharpness reconstruction and satisfactory reconstruct results compared to other SOTA methods. Thank you for your attention.